Okay, here we go. So, I tried to make a video of the Spike's Ferris video that he made the other day. It is Distant Starlight and Biblical Creation Part 1 and Part 2. I think I showed the Part 2. But I want to go to Part 1 because it explains it maybe perhaps a little bit better. So hopefully I can do a better job of explaining about the time light problem being resolved by actual science and general relativity. So, and there's a lot of things that we're considering. Hello, Christian Carpenter. How you doing? Hope you're having a good Friday. Yeah, I'm doing pretty good. Yes, and I'm just going to relax a little bit after this video. So let's jump into it and see what's going on here with this video with Spike Ferris here. Okay, here we go here. And we'll make it larger so I can see it. And we'll go ahead and play it.
We'll talk about that in more depth in your November meeting. Now, to this point, I have discussed two proposals that, to various degrees, invoke miraculous processes. And a lot of people are hoping to have explanations for the LTT problem that are a little more concrete and a little more explicitly invoking of science and scientific principles. So that's what the next.
Okay, so this is very important because, well, for one thing, you can't just invoke miracles all the time, obviously, when we have an actual creation. And there's still a few problems, but they're not too problematic considering that there was a creation of everything, the sun, moon, the stars, everything. That means the entire sun was created, the entire moon was created, and the stars were created, and it was on the first day. So we go from a working sun, a shining sun, shining stars on the first day. Because in the beginning, God created the heavens and the earth. And the heavens and the earth means every physical thing without being made into life yet. And then the earth was formless and void, and it was covered with water. And there was darkness over the surface of the deep, and then there was light. So there was darkness, then there was light, but then the sources of the light were made to be seen on the fourth day. But, you know, a lot of people will say, well, God used a substitute light until the sun was created. I don't think that's necessary. That's still invoking a miracle after everything was already made. You know, the sun, the heavens and the earth were already made. But anyways, let's not dwell too much on this.
From here on, that's what we'll be doing. The third proposal is called the variable speed of light, VSOL. Back to our formula. Now we're challenging the speed again. If the speed of light were variable and not absolute, then that would change the amount of time required for light to travel distance.
Okay. And I've been through this before, but I don't think, not even so sure that everyone's understanding it correctly. Okay, we have a speed. Light travels from point A to point B in a certain amount of time at a certain speed. In order to determine the speed, you have to know the time it takes to travel from point A to point B, and you have to know the distance that it is from point A to point B, both of which affect the speed of light. So let's say point A is 0 and point B is 186,000 miles away. So, and we're just saying within this frame of reference that we're talking about, that's 186,000 miles long, and the rate of time is passing by, let's say, the same rate as it passes by where we are today. I mean, where we are inside of on the Earth, inside of the galaxy. Okay, so we have a rate of time, which is basically we'll use 1 second. It takes 1 second for light to travel from point A to point B, which is 186,000 miles. 1 second, so it's a thousand one. That's the speed which the light travels. It's 186,000 miles. 1,001. 186,000 miles a second. That's the rate of time where we are. And it's the rate of time everywhere in the universe, too, with a caveat. The caveat being that time is not always the same rate. Time can be slower. It can be 1,001. Time can be faster. 1,001. And the distance can be smaller. So let's say we're near a black hole. We have point A, point halfway between point A and point B. I should have said point A, B, and C. But halfway between point A and point B, we have a place, a distance. And let's say we're closer to the black hole. So the black hole contracted the distance. So the distance is no longer 186,000 miles, and no longer from point A to point B. 186,000 miles was contracted. This point B, which is the same point B, is shrunk down to here. So this now we have the point A to point B. Yeah, that's correct. And which is a smaller measure of distance, but it's still 186,000 miles. It's just that the 186,000 miles shrunk because you're closer to a black hole. And what's going to happen to time? Time is going to go slower. Time is going to go slower. The distance is contracted. What's the speed? Tell me if the speed is faster or slower going from point A to point B. 1,001. Is that the same speed as 1,001? Or which one is faster? 1,001 or 1,001? It's the same distance. It's the same second, only the second is slowed down and the distance is contracted. So what happens to the speed relative to where we are? And say we're looking at this, we're looking at a place near a black hole, and we watch the light go from point A to point B. It's still point A to point B. It's 186,000 miles. Our 186,000 miles is this big, all the way across, right? But the 186,000 miles where we're observing is actually half as big because it's closer to the black hole. And time is going slower, and so we see the light. Now we see the light going 1,001. That slowed down the speed of light because where we are, it's a larger measure of distance and a faster rate of time. So it's 1,001. That speed is faster. Now near a black hole, the speed is slower, 1,001. See how that works? You have to do these thought experiments to understand general relativity. This is what's happening. Now, conversely, if you're away from a galaxy, Then the measure of distance is greater, is say it's twice as big as the screen, and the rate of time is going by faster. So then, how fast is the speed of light then? Thousand, thousand. I don't even know if you can see the arrow. Thousand what? It's even faster, right? So tell me, Mr. Einstein, is the speed of light constant or not? Or is it just a mathematical construct? It's a mathematical construct. Within the frame of reference, it's always the same speed. It's always 186,000 miles a second. But when the second slows down and the distance gets shorter or smaller, the same distance, 186,000, gets crunched up near a black hole, it's going to slow down the speed of light. So the speed of light is absolutely not constant, is what the point is. And I can't believe they don't teach this in school.
Now, you may be scratching your head and saying, wait a minute, we already talked about speed of light decreasing over time, and you said it didn't do that. Correct. This is not a proposal that light has decreased its speed over time. This is a proposal that its speed varies by location. Specifically, how much gravity, the strength of the gravitational field in a particular location. After all, where have we ever measured the speed of light? All of our measurements have been done where? In the solar system. Mostly on Earth, a few farther out. We've never measured it outside of our solar system. Every measurement we've ever had, or ever made, has always been within the gravitational field of the sun. I mean, we only have a few spacecraft that even left the solar system. That happened very recently, and they're decades old and aren't set up to measure this.
Okay, now he's even not even considering outside of the galaxy. It's not yet. But he's talking about outside the solar system, where the gravity is less. So of course, the speed of light is going to be faster outside of the solar system, but according to superluminal motion, it gets even faster. They measured with our measure of distance. They measured superluminal motion, that is a plasma jet, which is it's not even light. It's a plasma shooting out from the center of a galaxy. They measured it to be moving 7 times the speed of light. Now you know that's just nonsense. It's their measures of time and distance are off. Because as the plasma shoots out of the galaxy, now it's outside of the galaxy, moving in a place where there's a lot less gravity, where time is passing by faster and distance is greatly expanded, meaning it's less distant. It's less distance than what they thought it was. That's why they got a thing of 7 times the speed of light. And I don't even know if Spike Ferris is even going to mention the dilation of distance. He mentions the dilation of time and questions the speed of light, but I don't know about. A lot of people forget about distance too, which even compounds magnifies the effect.
So if all of our measurements are done within the sun's gravitational field, what is the speed of light outside of a star's gravitational field? We don't know. Never measured it. We assume it's the same, but that is just an assumption. If gravity were to slow light down, number one, we wouldn't be able to notice it because we have only measured it here. Number two, that would change the time required for light to travel long distances, right? Because between stars, there's less gravity. And between galaxies, of course, you'd have vast distances with nothing.
There you go, galaxy, between galaxies, you mentioned it.
Producing a gravitational field. So conceivably, if this idea were true, light would be able to travel much farther distances over much shorter periods of time than is commonly thought.
And the distance is not as far as what they measure it to be. It's not as far. So it takes less time to travel the distance, plus the rate of time is going faster anyway. So it compounds the effect.
Many people have noticed that space-time behaves as a fabric. Mass distorts the fabric of space-time, and that's what we call gravity. And we can talk more about that in Q&A if this is a new concept to you. But many people have noticed that the equations describing this are very similar to the equations that mechanical engineers use to measure the deformation of a fabric under stress and strain and so on. And we know, incidentally, from this, that mass and gravity will change the path of light through space-time. You know, light will bend around massive objects, even though it has no mass.
So, I have to address this too because Gravitational lensing is from bending light. Yes, it's from bending light, but it's not so much the effect of bending, it's the effect of traveling through a space that is much more contracted, where time also slows down, which slows down the passing of light through that space. Sure, it bends light. We know that a lens bends light, and this is what happens in gravitational lensing. It's bending the light, yes, but it's not only bending the light. The reason why it magnifies the object is because of the bending of light, but because through one part of the lens, light is traveling slower, and through another part of the lens or space, light is traveling faster, which is exactly what a lens does and is. And so it's not only bending light, because skeptics will say, "Oh, it's just bending light." No, it's not just bending light. It's actually slowing the light down in the middle, and is slowing it down not so much on the outer edges, which is what makes a lens. That is a lens. That's what a glass lens does. It slows down light in the middle and not so much around the edges. And that's what the magnification is. That's what causes the magnification. That's what gravitational lensing is.
So we know gravity already affects light in that sense. What if, in addition to changing light's path, it also changes light's speed? That being the case in deep space, as I said, potentially light could travel much more quickly, which would solve the LTT problem. I've had this idea in my creation talks for quite some time now. I was encouraged when the
I like this. He's had this idea for quite some time now. I've had it for quite some time now too. And now he's encouraged because somebody's wrote it up in a paper. And but I'm glad. I don't need to get the credit for it, but I'm just glad people are considering it and talking about it. Except they don't seem to be talking about the expansion of distance, making it less distance yet. That I didn't see anyway.
most recent ICC conference, there's actually a paper digging into this idea in more depth and actually making it more formal and mathematical proposals that can be investigated further. So I'm hoping that the creation movement overall will start paying more attention to this. I'll also note that we are not the first ones to do so. Secular cosmologists, at least some of them, are also investigating this idea. There are certain secular cosmologists who would love to have light speed be variable to solve certain problems that they have. My point is, this is not only a proposal that on our side of the thing, there's scientists across the spectrum that are looking into this as a viable.
But every time I talk to skeptics and secular scientists, they deny that this is a thing. This variable speed of light, VSOL, variable speed of light, among secular cosmologists. Of course, it's secular. Oh, they're talking about modified gravity and all this stuff, but that's just a smokescreen. The problem is that there's no single measure of time or distance in the universe. Everything runs at a different rate of time. Everything is a different measure of distance. It's the same yardstick, only the yardstick in outer space is twice or three times or 10 times as big. And then the same yardstick near a black hole is only like a centimeter big by comparison. And it's a fact that the distant galaxies that we see with the infrared James Webb telescope, those distant galaxies that we can't even see with visible light, those galaxies are closer than our own black hole Sagittarius A. Maybe I have to repeat that. The most distant galaxies are closer to us than our own Sagittarius A black hole. The center of our black hole is farther away than the most distant galaxies that we observe with James Webb telescope. That is what general relativity predicts and observes. I mean, that's what the observation is, and that's what it is. Because general relativity is not just a theory anymore, it's been observed. Time dilation is observed, and you may or may have not have noticed, but with the interferometers, where they detected gravitational waves, was the first time in human history that they detected a variation in distance. It wasn't much variation in distance because it takes a lot of power to do that. It takes a lot of energy to do that. But they did detect a variation in the measure of distance. So general relativity is not just a theory anymore, it's an observation. So people that want to deny general relativity and stuff, it's now an observation with the gravitational waves. And of course, we've known for a long time that there's no single rate of time. That time's all different, runs at all different rates. Clocks run at all different rates. We've known that for years. Many years. I mean, we've observed it for many years, but now we've observed the dilation of distance as well, which confirms general relativity.
Possibility to explain certain things. So, variable speed of light is option 3. Option 4 is the anisotropic synchrony convention, known as ASC. That's quite a mouthful, isn't it?
Okay, that's another idea, which I'm not too much in favor of. But anyways, that's what it that's what it was. Just a little better review maybe of of my observations in science. And here we go. We got lots of people going on here. Look at this. Okay, we got Alec. We got Brother Timothy. And Alec, Christian Carpenter. Time is relevant to perspective, very difficult for non-mathematical minds to grasp. Curve. Yeah, I'm hoping that I was able to explain it well, because I don't think. I mean, it took me a while, but I had to think about it. I had to do all the thought experiments to understand general relativity. But yeah, there we go. So I guess that's about it. Again, the speed of light is not constant. I know Albert Einstein wanted everybody to understand or believe that the speed of light is constant. No, it's constant in a mathematical construct. But if you have different measures of time and distance, no, it's absolutely not constant, especially with the effects that are compounded by the measure of distance. I hope everybody understood it. It's very hard to explain, but I thought JJ did an excellent job. Okay, that's good. Excellent job of trying anyway. But it's not only time runs faster, the distance is more expanded, so the light travels even faster. So the light arrives even faster, especially if there's no gravity. What happens if there's no gravity? There's no gravity, light arrives instantaneously, instantly. There's no gravity in outer space, and the little gravity that there is canceled out from all the galaxies all around pulling on each other, and that's another thing with the redshift, which is a possibility. Let me just go ahead and do this. The redshift, I was thinking about it because it's another thing. Light is redshifted as the light leaves a galaxy. That's just the effect of the general relativity. As light leaves the galaxy, light is redshifted. Then when light enters a galaxy, like where we are, it's blue shifted again. So it's back to normal. So it's red shifted and back to normal. Red shifted and back to normal. No matter what. The more massive galaxies, obviously, are going to be more redshifted because they're more massive compared to our less massive, smaller galaxy, which is not going to blue shift it back to its original wavelength, right? But check this out. I've been thinking about redshift for a while. And so not only do we have this effect where the most distant galaxies that we see are all massive galaxies to begin with. We're only seeing the extremely massive galaxies. And of course, the light is redshifted as it leaves the galaxies and only slightly blue shifted back in our much smaller galaxy. And we're not even in the center of the galaxy, where most of the light is coming from on these galaxies. But consider this, consider the idea that there's a lot more mass from the origin of the light, from the origin of the galaxy. There's a lot more mass out there than there is where we are. And because, I mean, as far as what would be, you know, pulling on the light. So that greater mass out there of all the galaxies out there, the greater distance is probably what's redshifting the light. That the farther away it is, the more the light travels between all these galaxies, the more galaxies the light has to pass through, so the more the light is redshifted. That's I just thought of that today. So that's probably what's causing the redshift anyway. So fear not, the saints of God. Did I say that right? Oh, fear not, you saints of God. Anyways, fear not, you saints of God. There's nothing to worry about, nothing to make you feel afraid, nothing to make you doubt. Remember, Jesus never fails, so why not? No, it's cheer up. There you go. Fear not. No, I'm saying something wrong. Cheer up, you saints of God, which is even better, right? Cheer up, you saints of God. There's nothing to worry about, nothing to make you feel afraid, nothing to make you doubt. Remember, Jesus never fails, so why not trust him and shout? You'll be sorry you worried at all tomorrow morning. And the skeptics are only looking for excuses. They're not looking at the facts, they're looking for excuses. They're looking for reasons not to believe. You know. Anyway, that's about it, I guess, for right now. Let me see. It's not hard for those who have mathematical mind, but impossible who don't. I tried all week to teach a smart young man to measure who just couldn't grasp the concept. Yeah, it takes time. I mean, even the thought experiments in general relativity take time. So it's just a matter of thinking about this every day, which is what I would do. I'm thinking about it at work. I think about this. Well, what about this problem? What about that? What about this? The other thing. Now, I could have solved the redshift problem just now. You know, because if you think about it, you know, the farther away the uh, the light source is, the more mass there is between it and us, which is probably what's causing the redshift. Considering the fact that light is redshifted leaving the galaxy and blue shifted coming back into a galaxy. So, anyways, that's about it for that. God bless everybody. Take care. And see you on the flip side. I don't know if people even know what that means anymore. See you on the flip side. Uh, God bless. Take care.